Hey there, fellow explorers! Welcome to another exciting journey into the world of physics. Today we're going to explore how physics isn't just a subject you study in school, but a fascinating part of our everyday lives. Today, we're diving into the fascinating world of physics, and you'll be amazed at how much it influences everything around us. From the moment you wake up to the time you go to bed, physics is at play. But don't worry, no textbooks or lab coats required. We're going to make this fun and relatable. Imagine discussing the wonders of physics over a cup of coffee with friends, or laughing about it in a casual setting. We're going to uncover the secrets behind everyday actions like pushing a shopping cart or flipping a light switch. Have you ever thought about the forces at play when you do these simple tasks? And see how these simple acts are governed by the fundamental laws of physics. For instance, when you walk or drive, you're constantly interacting with the laws of motion and energy. Ever wondered why it takes more effort to push a heavier object or why some cars accelerate faster than others? These everyday observations are perfect examples of physics in action. The answers lie in the concepts of work, energy, and power. These principles help us understand not just mechanical systems, but also how we use energy in our daily lives, from sports to household chores. These principles are not just abstract theories confined to textbooks. They are the invisible forces shaping our world. Every time you interact with technology or navigate through a busy city, you're experiencing physics firsthand. So buckle up and get ready to see the familiar through the lens of physics. Whether it's the thrill of a roller coaster or the simple act of fastening your seatbelt, physics is there, ensuring our safety and enhancing our experiences. Let's unravel the mysteries of the Work-Energy Theorem and Power together. By the end of this journey, you'll have a newfound appreciation for the physics that makes our world tick. So, let's get started. We often use the word work to describe our daily tasks, but in physics, work has a specific meaning. Imagine pushing a heavy box across the floor. You're applying a force on the box, and it's moving a certain distance. That, my friends, is work. In simple terms, work is the force applied to an object multiplied by the distance the object moves in the direction of the force. It's like a measure of how much effort you put into moving something. The greater the force, or the longer the distance, the more work you do. So, next time you're pushing that shopping cart down the aisle or lifting weights at the gym, remember, you're a physicist at work. Now let's talk about energy, specifically kinetic energy. Everything that moves possesses kinetic energy. It's the energy of motion. Think of a speeding car, a flying bird, or even a spinning top. They all have kinetic energy. The faster an object moves, the more kinetic energy it has. Similarly, the heavier an object is, the more kinetic energy it possesses at the same speed. It's like saying a bowling ball rolling down the lane has more kinetic energy than a tennis ball moving at the same speed. Kinetic energy is all around us, from the smallest particles to the largest celestial bodies. It's the energy that keeps our world in motion. Now here's where things get interesting. The world of physics is full of fascinating connections that help us understand how things work. One such connection is the Work-Energy Theorem, which beautifully links the concepts of work and kinetic energy. This theorem is a cornerstone in the study of mechanics and helps us understand the relationship between the forces we apply to objects and the energy those objects possess. The Work-Energy Theorem states that the work done on an object is equal to the change in its kinetic energy. In simpler terms, when you apply a force to an object and move it, you're doing work on it, and this work translates into a change in the object's kinetic energy. Let's break it down with an example to make it more relatable. Consider a common scenario that most of us have experienced. Imagine you're at the supermarket and you start pushing a shopping cart. Initially, the cart is at rest, and you need to apply a force to get it moving. As you push the cart, you're doing work on it. This work increases the cart's kinetic energy, causing it to move faster. The harder you push, the more work you do, and the faster the cart goes. However, if you stop pushing, the cart will eventually come to a halt due to friction between the cart's wheels and the ground. This frictional force does negative work on the cart, reducing its kinetic energy until it stops. This principle also explains why it takes more work to stop a heavy truck than a small car moving at the same speed. The truck, being much heavier, has more kinetic energy. Therefore, you need to do more work to bring the truck to a standstill compared to the car. This is why larger vehicles require more powerful brakes and longer stopping distances. Understanding the work-energy theorem not only helps in academic studies but also in practical applications, such as vehicle safety and engineering. It's a fundamental concept that connects the dots between force, work, and energy in the physical world. Section 5. Power, the need for speed of doing work. Power is all about how quickly work is done. It's a measure of efficiency and effectiveness in various tasks, whether it's in a bustling office or a high-speed factory floor. The faster the work is completed, the more power is being utilized. It's the rate at which you transfer energy. This concept is fundamental in both mechanical and electrical systems. For instance, in mechanical systems, power is transferred through movements and forces, while in electrical systems it's transferred through currents and voltages. Think of it this way. Running up a flight of stairs requires more power than walking up the same stairs, because you're doing the same amount of work in a shorter amount of time. This is a simple yet powerful illustration of how power works in our daily lives. In simpler terms, power is the amount of work done divided by the time it takes to do it. This equation helps us understand and quantify power in various scenarios, from everyday tasks to complex industrial processes. A powerful machine can do a lot of work very quickly, like a crane lifting a heavy load in seconds. This ability to perform tasks rapidly and efficiently is what makes powerful machines indispensable in construction and manufacturing. From the horsepower of your car's engine to the wattage of your light bulb, power plays a crucial role in our lives. It determines how fast your car can accelerate and how brightly your light bulb can shine. Understanding power helps us appreciate the technology and engineering that make our modern conveniences possible. Section 6. Complex systems, from roller coasters to light bulbs. The principles of work, energy, and power apply not just to simple actions, but also to complex systems. Take a roller coaster, for example. As the coaster climbs the first hill, a motor does work to increase its potential energy. As it races down the hill, this potential energy converts into kinetic energy, giving the coaster its thrilling speed. Similarly, in an electrical circuit, a battery does work to move electrons, generating electrical energy. This energy then powers our devices, from light bulbs to smartphones. Understanding these concepts helps us design and optimize complex systems for efficiency and performance. Section 7. Efficiency. Why we can't escape friction. In an ideal world, all the work we put into a system would convert into useful energy. However, in the real world, we encounter a pesky thing called friction. Friction is a force that opposes motion and converts some of the energy into heat, which is often wasted energy. Think of rubbing your hands together. You're doing work, and you feel the heat generated due to friction. This heat represents the energy lost due to friction. Efficiency is a measure of how much of the input work converts into useful output work. Engineers strive to design machines and systems with high efficiency to minimize energy loss and reduce waste. Section 8. Real-world applications, engineering our world. Engineers use the principles of work, energy, and power every day to design and optimize everything from cars and airplanes to power plants and medical devices. They calculate the power required to lift an elevator, design aerodynamic cars to reduce air resistance, and develop energy-efficient appliances to conserve electricity. Understanding these concepts also helps us make informed decisions about our energy consumption. By choosing energy-efficient appliances, driving fuel-efficient cars, and conserving energy at home, we can reduce our carbon footprint and contribute to a sustainable future. The next time you come across a marvel of engineering, remember the invisible forces of physics that made it possible. Section 9. Conclusion. Keep exploring the universe of physics. So, there you have it, a glimpse into the fascinating world of work, energy, and power. We've seen how these fundamental concepts govern our everyday lives and explored their applications in complex systems. Remember, physics is not just about equations and formulas, it's about understanding the world around us. It's about asking questions, seeking answers, and never stopping to explore the universe and its wonders. Keep questioning, keep exploring, and keep the spirit of scientific inquiry alive. And hey, if you have any questions or comments, feel free to drop them below. Let's keep the conversation going.